This is the rocket science section of our aeronautical engineering course, part 1. Rocket science deals with actions and reactions, and we have actions and reactions with airplanes too. Propellers, they blow air backwards, and that makes the airplane go forward. So it's good to understand these concepts. So before we talk about our rocket science, let's familiarize ourselves with force and weight and mass and pounds and kilograms. Here's a bottle of strawberry fruit spread. It says net weight 20 ounces, 1 pound 4 ounces. Okay, that's what it weighs, but it has a mass of 567 grams. Okay, and here's some pink lemonade. Let's see, it has a weight of 1 pound 3 ounces, and it has 538 grams of mass. Okay, what if we were to take this strawberry fruit spread and this pink lemonade into outer space? Would it still have the same weight? Would it still have the same mass? Well, it would indeed still have the same mass, but its weight would be a lot less, because the further you get away from Earth, the less weight you have. Its weight would be so low that the centripetal force that would be acting upon it, because it's going in circles around the Earth, would counterbalance the weight, and thus it would be in orbit, like the International Space Station or those satellites that we have out there. Okay, but as a general rule, we equate weight, pounds, with kilograms, even though pounds change when you leave the Earth's surface, but kilograms don't. Okay, generally speaking, 1 pound equals 2.2 pounds equals 1 kilogram. Let's see if that's true. Here's according to Google, if you look it up, 1 pound equals approximately 454 kilograms, but the most right answer is 1 pound equals 453.59237. That's a pretty exact answer. Let's see, here's a box of rat poison. It says net weight 5.6 ounces, and there are 8 20-gram blocks here. Let's check that out. 5.6 ounces. Well, there's 16 ounces per pound, so divided by 16 gives us 0.35 pounds. Okay, and there are that many grams per pound, so times 453.59237 equals 158.75, almost 159 grams. It says there are 8 20-gram blocks. That'd be 160 grams. Sounds like the rats got shorted 1 gram, but I haven't heard any of them complain. Okay, let's take a look at a guy throwing a baseball and standing on a skateboard. Okay, let's see. Here's a skateboard, and here's the wheels, and here he is standing on it, and he's got a baseball. Let's say he's throwing a baseball 100 miles per hour. And let's say he's throwing 1 baseball per second. Okay, so that means the baseball starts out here, it's going 0 miles per hour. But by the time he releases it, it's going 100 miles per hour. So its average speed is 50 miles per hour. You know, for an incrementally small amount of time, it's going from 0 to 0.001 miles per hour. For the same amount of time, it's going from 99.999 miles per hour to 100 miles per hour. It spends just as much time going close to 1 mile per hour that it spends going to 99 miles per hour. You can say the same for 75 and 25 miles per hour, for 51 and 49 miles per hour. What I'm getting at is that it averages 50 miles per hour. So let's figure out how many feet per second 50 miles per hour is. Okay, 50 miles. Well, there are 5,280 feet in a mile, so 5 times 5,280 equals that many feet per hour. Well, there are 60 minutes in an hour, so divided by 60 equals that many feet per minute. And there's 60 seconds per minute, so divided by 60 again equals 73.333333. In other words, 73 and a third. Okay, 50 miles per hour equals 73 and a third feet per second. Okay, that's its average speed from the time he starts pushing on it back here to the time he releases it with his hand. So if it averages 73 and a third feet per second for 1 second, he has to have 73 and a third feet of length here to accelerate that ball 100 miles per hour. So he needs to have arms that are about 40 feet long. Of course, we know baseball pitchers have arms a lot shorter than that. And in real life, they're accelerating a baseball a lot more than 100 miles per hour per second. Baseballs weigh between 5 and 5 1/4 ounces. Okay, so there's 16 ounces in a pound. So let's say a 5-ounce baseball, 5 divided by 16 equals 0.3125 pounds. Okay, times 454 grams per pound, that would be about 142 grams. Okay. Yeah, let's try a 5 1/4 ounce baseball. 5.25 divided by 16 equals that many pounds, times 454 grams per pound equals 149 grams. Okay. Since they're somewhere between 5 and 5 1/4 ounces, we'll just say our baseball weighs, or not weighs, but has a mass of 145 grams. Pick us a number somewhere between those two. Okay. Okay, and here's the most fundamental equation in the study of physics. Force equals mass times acceleration. If you had a couple of balls, one in each hand, one's a golf ball and one's a ping pong ball, you pull both arms back and you throw both the balls with the same acceleration, with the same speed, leaving both of your hands, it'll take more force to throw the golf ball than it'll take to throw the ping pong ball, because the golf ball has more mass. If the acceleration is the same for each ball, but the mass is greater for the golf ball, well, the force will be greater to throw the golf ball. And if you are unfortunate enough to be hit by both a golf ball and a ping pong ball going the same speed, the golf ball will hurt more because it'll take more force to decelerate this greater mass. So let's get back to our man on the skateboard here. Okay, force equals mass times acceleration, where mass is 145 grams. That's what the baseball weighs. Okay, our acceleration is 100 miles per hour per second, because this baseball player is taking 1 second to accelerate a baseball from 0 miles per hour to 100 miles per hour. So, force equals MA equals 145 grams times 100 miles per hour per second. Alright, we'll have to use a few conversion factors to get these units the way we want them. The metric system is about the only system we know anymore when we're doing physics. So anyway, this is, our force is 145 grams times 100 miles per hour second. So that would be 14,500 gram miles per hour second. Yeah, I'm sure you've never heard of gram miles per hour second. It's not the term you hear every day. But we'll turn it into newtons here in a minute. When we multiply this figure by 1, it doesn't change. So let's multiply it by our conversion factors, which is the same as multiplying by 1. So if we multiply this times 1 kilogram per 1,000 grams, 1 kilogram per 1,000 grams, okay, and we multiply it by 1 hour per 1 hour per 3,600 seconds. Okay, and 5,280 feet per 1 mile, and 1 meter per 3.281 feet. 3.281 feet. Okay, what we then have is 6.48208 kilogram meters per second squared. Let's see if this all adds up. We've got gram miles per hour second times kilograms per gram. There's grams there and grams there, so they cancel out. Let's see, we got hours there and hours there. They cancel out. Let's see, we've got miles here divided by miles here, so they cancel out. We've got feet here and feet here, they cancel out. We're left with kilogram meters per second squared. Okay, of course we don't draw lines through all these numbers here, we still multiply all of them. Let's see if we can get the right answer here. Ooh, we don't really have time. But anyway, if you multiply 14,500, divide it by 1,000, divide it by 3,600, multiply it by 5,280, divide it by 3.281, you ought to get 6.48208 newtons. A kilogram meter per second squared equals a newton.